Hello and welcome. This is a further pure one AS further maths video. In this video, we're going to be going over something called complex conjugates, and the multiplication, addition, and subtraction of something else we call complex numbers. I did go over that in my previous video for further pure, so we're going to be taking that a step further. But as I said, we're going to be introducing something called a complex conjugate, which is a lot easier than it sounds, and really just pointing out some tips and hints really that you need to pick up along the way. And then obviously I'll be going through some questions out of the classwork book. Okay, so first thing we're going to kick off with is what actually is, just to recap what a complex number was. Okay, so we said a complex number is a mix of a real number, so this is 1, 2, 3, 4, 5, 6, 7, whatever, could be 2,999.6754321 times 10 to the minus 2, so that's a real number. Probably the first one that came to your mind actually. Anyway, so a complex number we said is a mix of a real number and a imaginary number. So if we call it something, if we said it was z, and then a complex number might be an a plus bi, for example, and we said we got this from the quadratic equation where we had a plus or minus the square root of b squared take full raised c, and then this became negative, if you remember, over 2a, so it's b minus b. And then we use this and we said, okay, well if this is negative, we take negative 1 out and that becomes some kind of I, so it'd be like 4i, for example. So as I said, if you don't quite get that, there was a previous video on that, but as I said, we sort of went from using this idea to go to this idea, and we said an imaginary number was something that can't be done, so root minus 36, for example, you take root minus 1 out, and root 36, so root 36 and root minus 1 is root minus 36, so that is 6i, because I is root minus 1, remember. Okay, so that was just a little bit of a recap on what we did in the previous video. Okay, so what is a complex conjugate? So I'm going to go on to that just before we start going through the rest of the theory, because I think it's quite important. Okay, so a complex conjugate, so okay, if we look at this, is z equals a plus first and then or minus bi. Then a complex conjugate of this, so this is a complex number, this is a complex conjugate, so you always have a complex number and a complex conjugate. We normally call this z star, because it's special, equals a minus or plus bi. Now you can think of this in the same way, you know when you have the addition form, oh well, you might not. If you've done C4, I'm not sure where you've done, but if you've done something called the addition formula, where you have the cos a plus or minus b, and then that is equal to cos a, cos b, minus or plus sin a, sin b. Anyway, that's basically what it is just a complex conjugate is a complex number where the sign in front of the imaginary number, in this case bi, has changed from what it originally was in the complex number. Now if we take z and z star, not necessarily adding them together, we'll go into that in a minute. When we have z and z star, we call this a complex conjugate pair. So hopefully you see how this is a lot simpler than it sounds. So we've got a complex number, which we said is a mix of a real number and an imaginary number. Not one we pluck out, just one that math doesn't like, but you know, mathematicians like it. Anyway, and then we said when that's mixed with z star, which is the exact same number, exact same complex number, however the sign in front of the imaginary number has changed. When we have them two together, we call it a complex conjugate pair, because this is a complex conjugate, and this is what it started from, the complex number. So I think an example might be a bit more helpful. Now these don't have to work, so you might not see this in any book. So if we had z equals 3 plus 2i, in this case, because this plus is on the top, we're looking at what's on the top, as it changes to a minus, therefore the z star of this is equal to 3. That doesn't change, but it's minus 2i instead of plus. Okay, so this z and z star is what we know as the complex conjugate pair. Very similar to trying to show what's the above. So if we did it the other way round, so if it was say if it was 4 take 2i, because we changed the sign, therefore z star is equal to 4 plus 2i. Okay, so it's a very simple topic, very simple idea, that complex conjugate. This is called a complex conjugate pair. We have z, which is a complex number, and a complex conjugate. They are a complex conjugate pair. Now, it's very hard to understand what this word means, but when you see it in a format like this, you'll understand it's very simple. It's definitely nothing advanced. I think it's just trying to, so that people go, oh, what the hell does that mean? I have no idea. I'll give up. I'll throw the book at it. Because it's not. I don't think it's that difficult in terms of the actual theory. Okay. Now, I'm not sure. Can't exactly remember if I did some of this in my previous video. I mean, I could watch it, but that takes time. Obviously. So what we're going to be doing. So I mean, obviously, I'm going to be covering this on purpose so you understand where we're coming from. I'm going to be adding complex. Now, I'm not going to be adding complex conjugates because, well, we could do that, but it'd be the same method as adding complex numbers. And when we come to divide complex numbers, you might get a little bit confused because there is a slightly different method. But the rest of them apply exactly the same method. So if we've got a complex number, so I'm going to call this z1, and we say that's 4 take 2i, and we've got another complex number. Now this is not the complex conjugate, because it's a totally different complex number. If we have this as 8 plus 7i, and we want to do, we say z1 plus z2. So basically this is the same as saying in brackets 4 take 2i, and all of that plus 8 plus 7i. Really, it's just adding the like terms, as I put it. So what we do is we add the real numbers. When I say like terms, this is the same sort of doing. If you think of it as sort of x and x squared sort of thing, it might help, but you necessarily don't have to. So if we add 4 and 8 together, we get 12. Minus 2 plus 7i, that gets us plus 5i. So that's the answer to that one. Now if we had z1 times z2, we rewrite this equation as 4 take 2i times 8 plus 7i. Now instead of adding like terms, because we're timesing, you have to times it all out of the equation. Now we are going to end up with I squared, but if you remember, keep in your mind that I is root minus 1. That might help you. Okay, so what we're going to do is times out each term individually. So 4 times 8, which is 24. I made a mistake. Yeah. Well, 32. Let's see. You think I know that by now? And then minus 2 times 7i. Well, it's going to be minus 14i squared. But we can change that, and I'll come to how we change that in a minute. So this is minus 2i times 8, so it's minus 16i. 7i times 4, which is plus 28i. Okay, so simplify this down, so we get 32 is equal, so this is equal to 32 take, and because I is root minus 1, if we do root minus 1 times root minus 1, therefore we get minus 1. So it's minus 1 take away minus 1, so this becomes 14, so plus 14, because it's minus 1 times 14, so it becomes take away negative 14, which is, say, plus 14. So we simplify this down, so that becomes minus 16i plus 28i. So if we add them together, we get plus 12i. So if we simplify this down again, so that gets us 46 plus 12i. Okay, it's always good to keep the real number first, and I would always advise that. So just keep it in this kind of form. So we're going to be going over some more questions, but really adding and subtraction. So the reverse of these two follow exactly the same pattern. So if you're adding or taking, you add or take like terms. When I say like terms, this just means adding the real numbers and adding or taking away the imaginary numbers. Okay, when you are timing them together this is just two complex numbers. I mean, they could be complex conjugates, but we don't know that, so we just leave them because they would look exactly the same if they were complex. They wouldn't. I mean, obviously the sign in front of the I had changed, but we wouldn't be able to tell that. So I could have easily said, "Oh, that's a complex conjugate," but you might have got confused. So if you just imagine that, say, that's just a complex number. It's a lot easier to understand. But when you times or divide, oh actually no, not divide, no, we'll go on to that in a minute. So when you times complex numbers together, you times each term, not just like terms anymore, we're timesing the whole thing. Okay? Because this is the same, this is why I think of it. So if you, this is the same sort of thing as saying 4 take 2x plus 8 plus 7x, you wouldn't add the 2x and the 8 together. You wouldn't do that because that's 2 times something plus 8. You wouldn't go, oh, that's 10 times something when it's not, because that's not 8 times something. However, when you times it out, this is the same as saying, okay, 4 take 2x times 8 plus 7x. Okay? Then what you do is you times the 2x by the 8, because it's timesing, so they're going to have the same effect. So that's the way I think of it. If you can't quite understand why we just add the like terms here and take away the like terms, and why we times everything in this instance, why we times it, and hopefully if you did this, you would get the same sort of idea as this. Obviously, in this case, you won't be able to reduce the x squared to something because you don't know what x is, but it's just because we know the I, the imaginary number, is root minus 1, then we can get rid of the I squared because we don't quite like the look of it. We want it in the form a plus bi, because that's a complex number, so we want a complex number in the end. But this, it doesn't matter because it's just a quadratic thing. Okay? Right, so hopefully you understand that. Right, so what I'm going to do is, I'm just going to write what the complex number of something, well actually I'm not going to. So, what have we learned so far? Well, we've learned a complex number is a real number and an imaginary number. Should have already known that really. But a complex conjugate is it's a fancy way of saying the sign in front of the imaginary number changes. Now, it wouldn't sound very good. You're doing further maths, and this topic's called when the sign in front of the imaginary number changes. I mean, it might sound intelligent to some people, but generally most people in maths would go, oh god, whoa, don't take it to another level. Changing sign, that's advanced, that. You know, because we're doing further maths, they want to sound a little bit more intelligent than we actually are. So they say this complex conjugate. So don't get put off by the weird maths terms. You know, people who do maths generally, no offence, quite weird. As you can see, I'm doing maths and I can prove that point. Anyway, so going off track, I'm showing you some maths here. So anyway, we said when you add them, you add like terms, because I've shown you the kind of example of adding x's and numbers together. You wouldn't add the x and the real number together. You would add each like term. When you times them, that's a slightly different thing. Where you times out each term individually in the brackets. As again, you could think of that as being the x term. However, dividing, I like to think of it, divide is quite the I think personally it's slightly easier because you don't have to think about this expressions. You can think about how it actually is. So I'm just going to pick out a question from here. So I'll go through the questions, so I'm just going to pick out one. So the first one says 10, the first real number, so we'll call this Z1. So I'll do it in the format I've always been doing it. Now they might just the general write-ins format in the exam, but in my book they just write 10 plus 5i, but I'm going to call 10 plus 5i is the first complex number, and the second complex number, Z2, we're going to call that 1 plus 2i. And we're told to divide Z1 by Z2. Now, they could write this in a number of ways, but all looks the same. Generally, because they want to look intelligent, they'll write it like this, and that just looks a bit more confusing. But remember, it means the same thing. So therefore, you just write in 10 plus 5i over 1 plus 2i. Okay, so that's probably as far, I mean, they might rationalise in the exam, so you might not be able to get any further than the question in the exam. However, we have to remember what I actually is. Now, I actually is root minus 1. Okay, so if we were to write this, instead of replacing I with root minus 1, it would be 10 plus 5 root minus 1 and 1 plus 2 root minus 1. Now, as I said, I'm not sure where you've come up to with maths, but I'm assuming, even if you're in first year doing AS further maths in your first year, which is probably what most of you are doing, you will see, whenever you see, this comes from C1, so core 1, whenever you see a surd on the bottom, maths doesn't like that. Because it goes, oh, that's confusing, everyone's paddy ever paddy, he's not very happy. What you do is you do something called rationalizing the denominator. Now if we ignore this bit that we're actually trying to find out, because these two mean exactly the same thing, yes? Because we said I is root minus 1. So all I've done, really, is rewritten this equation and put I is minus 1. So what you do is you'd rationalise the denominator. So what you do is you do, okay, well you do this term on the bottom, but you change the sign here. Now that's key when related to this equation, but we're just going to go ahead and do it this way. So that's 1 take 2 root minus 1. 1 take 2 root minus 1. Because remember, it's the same as times it by 1, but we're just going to be able to get rid of this surd on the bottom. So if we follow this method, so we do expand the top out, so that's 10 times 1, so that's 10. 5 root minus 1 times 1, so that's just 5 root minus 1. I probably actually should have. Anyway, I'm just going to get myself confused. 10 times 1, 5 root minus 1 times 1, 10 times 2 root minus 1, so that's going to be take 20 root minus 1, if I've done it correct. So expand each term, so then we go 5 root minus 1 times 2 root minus 1, so the root minus 1 times root minus 1, they become minus 1, so it's 10. Basically this becomes plus 10. Okay? So you can do that in your own way. But on the bottom what we've got here is we've got 1 times 1, which is 1, the 2 root minus 1 and the 2 root minus 1 times together to get plus 4. Because obviously the 2 times negative 2 is negative 4, and the root minus 1 times root minus 1 is minus 1, so minus 1 times minus 4 is plus 4, and then we have plus 2 root minus 1 take 2 root minus 1. So this is going to cancel out the root minus 1s on the bottom. Now that's key when you remember root minus 1 is I, so there's going to be no i's left on the bottom. But as I said, I'm going to keep doing it in this form, so this is just going to leave us with 5 on the bottom. Okay, so then we add the top, so there we get 20 take 15 root minus 1. Okay, so what we do then is cancel this down, so 20 over 5 is 4, and 15 over 5 is 3, but this is minus 3, remember? So it's minus 3 root 1. Okay, now if we write 4 take 3 root minus 1 in terms of, because I is root minus 1, then we just replace the root minus 1 with I, so it's 4 take 3i. Okay, so you see how we've done this? So this is a division, by the way. All we've done is rewritten this equation in terms of I being root minus 1 and rationalised the denominator. So it's nothing new, really. If you've done C1, it's nothing new at all. You're just applying that concept to this imaginary number, which is really just a surd. So we used the same sort of rules for this. Okay, that's why I think it's a little bit easier to understand than the others, because you can see where we're coming from with it. Okay? Right, so if we apply the same method to this one, now we know how to do. So if this works, if I'm right, and obviously I am, we're going to get the same answer, so this is going to be 4 take 3i. So if we apply the same method, so what we're going to do is, we said we need to rationalise the denominator. So we change the sign in front of the surd, in front of the surd on the bottom. And now because this 1 plus 2 root minus 1 becomes 1 take 2 root minus 1. Therefore, because we can rewrite 1 take 2 root minus 1 as 1 take 2i, because that's the signs in front of the the imaginary number has changed. That's 1 take 2i over 1 take 2i. Expand this out as we did in the previous question. Okay, so what we're going to do is 10 times 1, which is 10, plus 5 times minus 2, so plus 5i times minus 2i is going to be minus 10i squared. And we can simplify that down like we did before in a minute, but leave that. 5i times 1, which is going to be plus 5i. Now I'm going to just group together the i's without missing it, sort of skipping off a step. So remember 5i and then minus 2i times 10, so it's minus 20i plus the 5i. It's going to be minus 15i. And that's going to be all over 1, and that's going to be plus 2i, take 2i, take 4i squared. So if we simplify that down, so the 10i squared, because I is minus 1, root minus 1, so I squared is going to be minus 1, so 10 minus 10, so it's going to be plus 10, so that for 10 plus 10 is 20, so it's 20 take 15i over, well, the 2i's cancel, so it's 1 take 4i squared, and its I is root minus 1 squared is minus 1, and minus 1 times 4 is minus 4, and 1 take minus 4 is 1 plus 4, which is 5. Okay, so if we simplify this down, look, it's exactly the same. This is exactly the same as that, but we've just kept the i's in there instead. Okay, so therefore this gives us the equation 20 take 15i over 4, so it's going to be 4 take 3i, which is exactly the same as what we had down there. So that's proof why we do this. However, in mathematical terms, how do we put this? Because you can't go into the exam, I mean they won't ask you, but you can't say, oh, it's rationalising the denominator, because that's not entirely what this is all about. Now remember, mathematicians want to sound a bit more smart than everyone else. Now, we change the sign of the bottom number, in terms of, we change the sign in front of the imaginary number on the denominator, or the second term that we're dividing. Now what did we learn at the start of this video that said one number, one complex number, and it's another complex, something else of that, has the sign change in front of the imaginary number? Correct, or possibly, yes, no, correct, yes, no, possibly, maybe not. What it is the complex conjugate. So, what this says in the mathematical terms is when you have a complex number divided by another complex number, the second complex number, or the denominator, that the denominator of the complex is the denominator, you times both the numerator and the denominator by the complex conjugate of the denominator. Now, that is the same as saying, when you do this, you rationalise the denominator. I think mine sounds a hell of a lot simpler. Basically, you just change the sign in front of the imaginary number on the bottom, what you're dividing it by. As you can see, it gives you exactly the same answer. I've got quite angry at this in the past. You have some anger problems, but I'll sort that out in another video with you, talk about that. But you're doing some maths here. Okay, so as you can see, that's proof that it works, and hopefully you'll be able to understand that. Okay, so we're doing for time. Yeah, so I'm just going to pause this video now and rub that off, and then, well, it'll be a few seconds, and then I'll get started on the second part of this video. We're going through some questions, so I'll be going through a further pure classwork book 1. As I said, for the rest of you that don't have that booklet, I'll just be going through some questions. There's only a couple, really. There's only another. Well, I'm going to be starting actually going with some examples of adding and taking times in complex conjugates, and then just another example of this kind of thing. But I might add myself a few more in. Okay, so thanks for watching. Hopefully it's been helpful and not a complete and utter waste of your life. although I'm sure that's what most of you will say. So thanks for watching. Hopefully I've been able to highlight a few things there about that. Sorry about the quality of the camera, by the way. Just the lighting today in good old Great Britain, it's not the best. So anyway, thanks for watching, and hopefully it's helped, and don't forget to comment or whatever you do on YouTube these days, and we'll see you in another video.